Hi, I'd like to share how Power Integration's Bridge 2 and Motor Expert Suite can help improve the efficiency and simplify the design of your motor control system. Field Random Control, or FOC, is one of the most advanced methods to drive permanent magnet synchronous and brushless DC motors. This control method provides us with the means to maximize the torque while minimizing its ripple. Let's review how the current information is used to maximize the torque produced by the motor. Three-phase current information is sensed in the inverter. We'll be going into detail regarding current sensing later in this video. From this current information, Clark and Park transforms are applied to break the current down into its components, which we can then examine and control in order to improve the performance of our motor. During operation, the stator current vector will be spinning at the motor rotational speed. The sensed three-phase current information are its components in the three-phase motor axis, U, V, and W. We use the Clark and Park transforms to represent the current vector in the stationary and synchronous reference frames. The moving Q line in the right diagram represents the quadrature current component. It is perpendicular to the rotor position and is the torque-producing current, while the other component, shown by the D line, represents the direct current and is the flux-producing current. We can modify the two components to maximize the torque produced. For example, the magnitude and orientation of the stator voltage vector, represented by the VS line, can be adjusted so that we can have the same amount of torque produced with lower stator current. You can see this by checking the VS line on the left and the right diagram. Rotor position is required for proper FOC operation. This is normally provided by a mechanical encoder. We can eliminate this sensor by using the current information with the rotor position estimation technique provided in the Motor Expert software. Now that we've discussed where the current information is used, let's talk about how the current information is sensed in the inverter circuit. Normally, you add a shunt resistor in series with the low side switch. However, this signal will be very small, so you would need to add a signal processing circuit that will provide amplification and offset. Now here's the exciting part. Bridge 2's lossless current mirror, also known as the IPH pin, simplifies the current sensing by eliminating the shunt resistor and the signal processing circuit that you added earlier. These are then replaced by a small signal resistor, which is connected directly into your controller's ADC. Our Motor Expert software includes a reconstruction algorithm that allows you to implement sensorless field-oriented control using the IPH pin signals. The reconstruction algorithm provides both positive and negative current information. Now, here are a couple of observations regarding traditional shunt-based sensing and IPH-based sensing. Because the noise in the current sense signal is also amplified by the signal processing circuit, IPH-based current sense signal is less susceptible to noise. As you can see from the left and right diagrams, the IPH-based signal would have 2 times the signal resolution than of the shunt-based signal. This improvement in the quality of the current information with IPH-based sensing resulted in improved system efficiency and simpler predictive maintenance model with higher accuracy. For more information, you can download my white paper from power.com.